On a single August day in 1944, German commanders watched in horror as 82% of their unstoppable V-1 missiles were blown out of the sky without a single British gunner scoring a direct hit. Sabotage, radar hacking? No, the tiny American device they believed was impossible had changed the war overnight. Along the northern coast of German-occupied France, radar stations responsible for tracking the V-1 flying bombs monitored the daily launches toward Britain. These sites, operated by Luftwaffe personnel, recorded altitude, speed, flight stability, and the expected trajectory of each missile as it crossed the channel. In the final weeks of June 1944, their routines appeared predictable. Hundreds of V-1 South launched from ramps near Pas-de-Calais, their pulsajet engines producing the recognizable staccato signal that German technicians had grown accustomed to tracing across their screens. But by early July, radar operators at several sites began reporting anomalies. Flight paths that should have remained stable were terminating abruptly. Operators observed that clusters of V-1 South simply disappeared from their scopes long before they reached the English coast. The disappearances weren't uniform. Entire waves seemed to fall out of the sky in rapid succession, as if an unseen force were cutting through the formations. Reconnaissance observers soon confirmed the irregularities. They reported seeing mid-air explosions where no British aircraft were present. Even more unusual was the pattern. The bursts occurred several dozen meters from the missiles, not the direct, catastrophic strikes associated with conventional anti-aircraft fire. The V-1 South were losing control immediately afterward, spiraling downward into the channel or into open countryside before reaching their intended targets. Within German command posts overseeing the V-1 offensive, the reports triggered immediate concern. The weapon had been developed and promoted under the assumption that its speed, low altitude, and small profile made interception extremely unlikely. Early calculations by German engineers suggested that the chances of a direct hit by British guns were negligible. Yet, the data arriving from France contradicted every prediction. High-ranking officers demanded explanations. Technical teams were instructed to inspect the launch ramps, fuel mixtures, and autopilot mechanisms. Investigators examined Walter gyroscopes for signs of misalignment or vibration-related drift. Others suspected sabotage at the production sites, especially as Germany increasingly relied on forced labor in its armaments industry. Commanders responsible for the V-1 program, including Oberst Max Wachel, ordered rapid diagnostic firings over German-held territory to determine whether mechanical failure could explain the sudden losses. Every test flight performed as expected. Engine pulses remained stable. Range was consistent. The gyroscopic guidance held true. There were no fuel inconsistencies, no structural defects, no evidence of faulty frames or warheads. The missiles behaved flawlessly until they crossed into airspace watched by British anti-aircraft batteries. As reports accumulated, the pattern became undeniable. The British interception rate was climbing at a pace German analysts could not rationalize. From barely a quarter of the missiles being brought down in the first week after D-Day, the rate had surged to levels that defied every model German planners had created. The question circulated through command rooms and intelligence offices alike. How were the British suddenly achieving the impossible? No one yet understood that the unexplained explosions were the first visible signs of a weapon German physicists had already dismissed as unattainable, a device they had labeled wissenschaftlich unmöglich, a weapon they believed could not exist. Across the channel, the consequences of Germany's newfound confidence were unfolding with brutal regularity. The first V-1 struck London on the 13th of June 1944. And within days the city was enduring a type of bombardment unlike anything seen during the Blitz. These were not manned bombers whose approach could be predicted, nor aircraft that might abort under pressure. The V-1 South arrived without warning, flying at roughly 400 miles per hour, their pulsajet engines producing the distinctive, uneven drone that Londoners quickly came to recognize. The sound itself became a psychological weapon. In streets already scarred by years of bombing, people paused whenever the coarse buzzing swept overhead. Families in shelters counted the seconds after the engine sputtered. The cutout meant the missile had begun its final dive. If the silence lasted more than a handful of heartbeats, it meant the impact was somewhere else. If it came sooner, the explosion could be dangerously close. Buildings shuddered with every detonation. Glass cascaded onto pavements, and rescue crews moved from one shattered street to the next as hundreds of civilians were killed or injured in the opening days. Each V-1 carried nearly a ton of Amatol explosive. The damage radius was wide, capable of leveling houses, tearing open streets, and igniting fires that spread rapidly through densely packed neighborhoods, even when they missed their intended targets. The psychological effect was severe. The drone overhead, followed by sudden silence, created an unbearable rhythm for those living beneath the flight paths inside Germany. The effectiveness of the opening attacks seemed to confirm what Adolf Hitler and the weapons chief overseer, General Walter Dornberger, had long argued. The V-1 was the quantitative solution to Britain's resilience. It required no pilot. It cost a fraction of a conventional bomber. It could be launched in large numbers, day after day, without fear of interception. Dornberger's engineers calculated that even if only a portion of the missiles reached London, the overall explosive tonnage would surpass that delivered during the height of the 1940-41 Blitz. Their confidence rested on calculations as much as ideology. At 400 miles per hour and flying between 2,000 and 3,000 feet, the V-1 occupied an altitude band awkward for anti-aircraft guns and difficult for fighters to approach safely. The low speed relative to jet aircraft of later years was fast enough to complicate firing solutions, yet slow enough that dive intercept angles were extremely dangerous. Early analyses concluded that direct hits from British guns were statistically improbable, requiring thousands of shells for a single successful strike. Luftwaffe assessments labeled interception hochgradig unwahrscheinlich, highly unlikely, for London. This meant the threat was not temporary. The British government understood that sustained attacks at this pace would strain civilian endurance, emergency services, and essential infrastructure. Shelters were reopened, transportation schedules shifted, and anti-aircraft crews redeployed to protect critical areas. But despite these efforts, Britain faced a problem that seemed without a clear military countermeasure. The V-1, arriving in waves, represented a type of attrition bombing that could continue for months. Every successful launch from northern France added to the pressure. Every failure to intercept reminded commanders that the missile did not need accuracy to inflict damage. It needed only volume. The stakes were unmistakable. If the bombardment continued unchecked, London's ability to function as the nation's administrative and logistical center could be compromised. Morale already worn down by 5 years of war was vulnerable to a campaign designed explicitly to exhaust civilian will. And yet, the missile the Germans believed unstoppable was about to face something they never imagined. The early British response to the V-1 bombardment revealed the limits of existing anti-aircraft doctrine. Guns positioned around London and along the southern coast relied on timed fuses, mechanical devices that required crews to manually set the detonation point on each shell. This system had been adequate against conventional aircraft flying predictable routes at comparatively slower speeds. Against the V-1, it became an exercise in precision under conditions that barely allowed for rational calculation. Radar operators tracking the incoming missiles relayed estimated altitude, speed, and direction to fire control units. Gunners then had less than half a minute to convert those readings into fuse settings, load the shells, and fire. Even small errors, a fraction of a second off in timing, a misjudged velocity, or a faulty reading under pressure meant the shell would burst harmlessly. In empty air, many did. Gun crews watched strings of puffs appear well behind the missiles or burst prematurely before the V-1 South even entered the kill zone. Reports from frontline batteries in June documented the same pattern: shells detonating too early, too late, or far off to the side. Misfires were frequent. Ammunition expenditure soared with little effect. Crews worked in shifts through the night, sweating over range tables and hurried calculations while the characteristic drone of the Pulsejet moved steadily overhead. The psychological strain added to the physical burden. Some batteries were firing thousands of rounds per day, with results that commanders privately described as frustratingly negligible. The operational reality was grim. Even if British crews performed every step correctly, the mathematics still worked against them. The V-1 speed compressed engagement windows to seconds. Its low altitude reduced vertical space for fire correction, and the missile's small profile made direct hits almost accidental. Technical assessments from Britain's own scientists acknowledged that the system was being pushed beyond its intended limits. No combination of discipline, training, or determination could reliably deliver the interception rates London needed. Within the city, the toll was mounting. Rescue workers moved from one damaged district to the next. Civilian fatigue deepened as shelters filled nightly. Government reports on morale warned that the population, having already endured the Blitz, was now facing a new kind of stress, shaped by unpredictability and the mechanical relentlessness of the V-1 campaign. Winston Churchill pressed military leaders for solutions, but the available technology offered no immediate remedy. And then, unexpectedly, the numbers began to shift. In late June, British interception rates rose beyond what earlier analyses had predicted possible. By early July, they jumped even higher. German intelligence units monitoring the results documented anomalies. V-1 South exploding midair, despite no recorded direct hits. Ammunition usage falling dramatically even as destruction rates climbed, and batteries reporting unusually efficient firings. Internal German memoranda included phrases that reflected disbelief. Waffen explodieren, ungetroffen zu werden, weapons exploding without being hit. Minimaler Munitionsverbrauch, extremely low ammunition usage. Physicists at Pienemann dismissed these reports outright, insisting the claimed performance was physikalisch unmöglich, physically impossible. But the data coming from the Channel front could not be ignored. Something had altered the balance between attacker and defender. Something that did not appear on radar, did not require perfect aim, and did not behave like any weapon the Germans had anticipated. Something invisible had entered the battlefield. The unexplained explosions over the Channel were the first visible trace of a secret the British had been asked to protect at all costs. The weapon altering the course of the V-1 campaign had not been developed in London or on the front lines in France, but in laboratories and workshops scattered across the United States. It emerged from an idea that had seemed implausible to anyone familiar with the physics of artillery. A shell that could detonate itself at exactly the right moment without human timing, mechanical settings, or direct impact. The concept had been championed years earlier by an American physicist, Dr. Merle Tuve, who had been recruited to lead the applied physics laboratory at Johns Hopkins University. Under his direction, APL became the center of a massive, classified effort to create a fuse that would allow anti-aircraft shells to destroy fast-moving targets that conventional methods struggled to reach. Tuve resisted proposals for improved timers or stronger explosives. His position was uncompromising. Stronger guns would not solve the problem. Faster calculations would not change the math. As he put it during wartime discussions, the solution required not a heavier projectile, but a smarter shell. The result was the variable time fuse, later known simply as the VT fuse. Unlike the mechanical time fuses used by British gunners at the start of the V-1 assault, this device responded to the target itself. It contained a miniature radio transmitter that emitted a steady signal as the shell traveled through the air. When the shell approached an object of sufficient size, such as the metal body of a flying bomb, the signal reflected back toward the fuse. A tiny receiver inside detected the change. The returning echo created a momentary shift in the electrical circuit, triggering the detonator at precisely the distance where an explosion would be most effective. To German physicists, this level of miniaturization was beyond the limits of 1940s technology. They had studied more than 24 proximity fuse concepts before the war and dismissed each as unworkable. The obstacles were obvious. Vacuum tubes, the heart of any portable radio system of the era, were fragile. The fuses would need to survive roughly 20,000 times the force of gravity when fired from a gun barrel. They would need to tolerate extreme acceleration and rotational spin, maintain stable electrical performance, and remain functional after traveling thousands of feet through rapidly changing air conditions. Making such a device small enough to fit into the nose of a standard anti-aircraft shell appeared impossible. Tuve's team refused to accept that verdict. Engineers at APL worked with scientists, machinists, and manufacturers to redesign the basic components of radio technology. They commissioned new vacuum tubes, miniature, reinforced, and shock-resistant, built through methods then considered unconventional. Sylvania Electric Company, drawing on expertise from hearing aid manufacturing, developed tubes capable of surviving the firing shock. A glass-encased battery was created that remained inert until the shell was launched. The shock of firing shattered the internal vial, mixing the electrolyte and activating the power source at the moment it was needed. But the innovation did not come solely from laboratories. Once testing confirmed the concept worked, the United States mobilized an industrial network that extended far beyond APL. More than 100 factories across the country took part in the production effort. Companies that had built radios, refrigerators, and consumer electronics shifted to manufacturing fuse components. Women entered assembly rooms to solder circuits, wind coils, and inspect microscopic parts under magnifiers. Many had never worked with electronics before the war, yet they became essential to the accuracy and reliability of each unit. Patriotism, personal sacrifice, and a sense of duty fueled an output that grew into the millions. The VT fuse that would soon detonate near the V-1s over the channel was the product of this combined national effort. Against every prediction made by German experts, the United States had created a device small enough, robust enough, and reliable enough to guide a shell to the perfect moment of detonation. America wasn't just building weapons, it was building what its adversaries believed to be impossible. The sudden rise in British interception rates marked the beginning of a fundamental reorganization of the nation's air defenses. The existing anti-aircraft layout had been developed for conventional bombers, not flying bombs traveling at nearly 400 miles per hour. To counter the V-1, British commanders guided by technical advisors and supported by American equipment reshaped the defense system into a new structure known as the Diver Belt, named after the codename Diver used for the V-1 attacks. This reconfiguration moved the bulk of Britain's heavy anti-aircraft guns from inland positions to forward sites along the southern coast. The objective was to engage the incoming missiles as early as possible, over open water whenever feasible, so that debris would fall harmlessly into the channel rather than onto populated areas. Dozens of batteries were redeployed, forming a dense line of fire stretching across Kent and Sussex. Movement was rapid. Crews shifted locations, dug new emplacements, and reconnected communications in a matter of days. The effectiveness of this new barrier depended not only on its positioning, but on the integration of advanced detection and tracking systems. Among these, the American SCR-58 for radar played a decisive role. Unlike earlier British radar sets that required manual interpretation, the SCR-584 used automatic target tracking. Once locked onto a V-1, the system continuously calculated its trajectory and relayed the data directly to predictor units that guided the guns. Human error was drastically reduced. Crews no longer needed to estimate speed or altitude under pressure. The machinery provided real-time solutions. With the introduction of the VT fuse, the transformation became complete. Gunners continued to load, aim, and fire, but the final task, detonating at exactly the right distance from the target, was handled entirely by the fuse. As long as the shells reached the general vicinity of the V-1, proximity would do the rest. The battle shifted from precision shooting to volume fire guided by advanced electronics. The impact became evident almost immediately as V-1 South crossed the channel. The first indication of the new defensive strength was the pattern of explosions. Observers along the coast described seeing multiple bursts around the missiles rather than the isolated puffs typical of earlier attempts. The sky often flickered with successive detonations as shells burst near the incoming weapons. Some flying bombs disintegrated mid-air, others lost stability and plunged into the sea. The rhythm of the engagements changed from sporadic fire to continuous rolling bursts that created an audible and visible barrier. In late August 1944, the Diver Belt reached its peak efficiency. On a single day, British defenses destroyed roughly 82% of all incoming V-1s. For German analysts tracking the results, the number was incomprehensible. Reports sent to higher command were filled with phrases like unmöglich, impossible, sabotage, and suggestions that British forces were using some newly invented deception to manipulate trajectories. None of these explanations accounted for the consistent results or the low ammunition expenditure accompanying them. The truth was simpler and far more damaging to German assumptions. The sudden collapse of the V-1 offensive was not caused by magic or trickery. It was the result of a technological leap that had fit into the palm of a soldier's hand. A fuse the size of a small flashlight, built in American factories, now determining the outcome of battles over the channel. The full impact of the Diver Belt and the VT fuse became clear within weeks. By early September 1944, the V-1 threat against London had been effectively neutralized. Of the more than 9,500 missiles launched toward Britain from ground sites in France and the Low Countries, only about 2,500 reached the city. The remainder were destroyed by fighters, barrage balloons, and increasingly by the coastal gun line, whose efficiency had transformed after the introduction of the proximity fuse. Casualties, though still significant, were far lower than German planners had calculated. More than 6,000 civilians were killed by the V-1 campaign, tragic in scale, but a fraction of the projected losses had the missiles continued hitting London at the earlier rate. General Frederick Pyle, Commander-in-Chief of Anti-Aircraft Command, later stated that without the VT fuse the number of deaths would likely have been 4 times higher. The device's contribution was not theoretical, it was visible in the survival of neighborhoods, in hospitals that remained intact, and in transportation and communication systems that continued operating. London emerged shaken but unbroken after years of enduring the Blitz. The city had faced another sustained air assault meant to undermine morale. Instead, the rapid improvement in defensive capabilities had the opposite effect. British newspapers reported the rising success rates. Civilians, who had grown accustomed to the sound of engines cutting out overhead, began hearing fewer explosions within city limits. Shelters still filled nightly, but the sense of helplessness that defined the earliest V-1 attacks began to recede. The improvement in defenses carried symbolic weight. Britain was no longer merely enduring the assault, it was countering it. For Germany, the outcome produced confusion and eventually introspection. After the war, when Allied technical intelligence teams examined captured German documents, they found no evidence that German leadership had ever identified the VT fuse as the cause behind the sudden failure of the V-1 offensive. Their scientists had considered proximity fuses before the war, but concluded that such a device would require technologies too fragile, too large, or too unstable to survive artillery launch. When Allied officers finally demonstrated an American VT fuse to capture German experts, reactions were uniformly astonished. Multiple accounts described the same remark. We believed this was 10 years beyond anyone's capability. The shock was not merely scientific, it reflected a broader contrast between the two wartime systems. Germany's armaments industry, under increasing pressure and constrained by rigid hierarchy, centralized decision-making, and chronic shortages, had focused on high-performance weapons that relied on precision engineering and specialized materials. The United States, by contrast, had mobilized a decentralized industrial base capable of mass production, rapid adaptation, and collaboration between universities, private companies, and government laboratories. Where Germany prioritized flawless prototypes, the United States emphasized scalable innovation. The VT fuse became a symbol of this divergence. It demonstrated how scientific cooperation, industrial flexibility, and the willingness to pursue a concept dismissed as impossible could generate battlefield change on a scale that exceeded the impact of many conventional weapons. Within the U.S. military, the fuse was ultimately regarded as the second most important technological achievement of World War II, surpassed only by the atomic bomb and strategic influence. Its legacy extended far beyond the V-1 campaign. The principles behind the proximity fuse shaped the development of post-war missile guidance, radar-linked fire control, naval anti-aircraft systems, and early surface-to-air defenses. The idea that a weapon could sense its environment and respond autonomously became foundational to modern munitions. The V-1 offensive had been conceived as a means to break civilian morale and disrupt British infrastructure. Instead, it triggered the deployment of a technology that reshaped warfare. London survived. German planners were confronted with the limits of their assumptions, and the global understanding of air defense was permanently altered. Sometimes the most powerful weapons aren't the loudest but the smartest. If stories like this help you see the war in a deeper, more human way, consider subscribing. It tells us to keep uncovering the forgotten chapters that shaped our world.